the circuit that I have up here on the breadboard, and we'll do it with electronic workbench. Oops. So I have a 2N3904. So we'll bring this down. And I think it's National Semiconductor. Okay, so it's 2N3904. Then on my, then we got 4 resistors, so I'll just pull them down and, oops, wrong thing, Rich. And these are our bias resistors. So we got one right here. Oops. And then we need one right here. This is our emitter resistor, right? And then we need one right here. This is our base resistors. Oops. Then we need a power supply. I'll bring a DC power supply up here. Common. Then we need an output capacitor. So our DC's on this side. This is going to be AC on this side. So what we do is we'll point the positive. It's a polarized capacitor, so we'll point the positive toward where our collector voltage is going to be. And then over here we'll do the same thing. So right here, what we'll do, my collector resistor is a 10K. And my emitter resistor is a 1K. And R1, what we generically call R1, is a 100K. And then this guy right here is another 10K. Okay, so what should our bias voltages be? We're looking for VB, VC, VE, and VCB. VCE. Sorry. While y'all calculating that, I'll go ahead and put a load out here. We'll load it with a resistor. So we got them yet? I'm still working on them. So what we got for VB? What's that? 1.1 volts. Yeah, on this we can just round to 1 decimal point. You should be fine. Because we got so many approximations going on. Everybody okay there? You okay, Joe? 1.1. So VB would be equal to VR1, which is going to be equal to 10K over 110K times, what was the voltage? How could y'all get 1 point? Okay, I didn't give y'all the voltage. Times 12, that's good. Where'd y'all get 12 volts from? Okay, that's good, that's fine. That was the default. I didn't put anything in there. That was good, but that'll work out. 12. So VB, which is VR2, I'm sorry, would be equal to 1.1 volts. Okay. And then what would VE be equal to? It's going to be equal to 1.1 minus 0.7, right? So what's that going to be equal to? 400 millivolts. Are we okay? Okay. Then IE is going to be equal to 400 milli divided by 1K, which is going to be 400 microamps, right? And we might need to change this up a little bit. Then VC, well, first of all, we probably need to calculate the voltage drop across the collector resistor. So VRC would be equal to 10K times 400 microamps, which would be equal to what? Four volts. Okay. And then DC would be equal to 12 minus 4 volts, which is going to give us 8 volts. Okay? That looks better. So what we probably need to do is change to get it closer, so we're biased toward cutoff, right? You understand that? So what would we need to do to bias this thing a little closer to the center, where we want it to be? What would I need to do? Huh? No, we want to lower the volts. What we have is that we have 12 volts to work with. Our ultimate goal is to get that sucker right there at 6 volts. Right? You understand? It's setting at 8 volts. The higher the higher the voltage on the collector is, the closer it is to cutoff. So that means when I bring an AC signal in or an audio signal in, if we get too high, the tops would clip before the bottoms. We'd like them to clip at exactly the same spot, right? And that would set our upper voltage we can put in. So what we need to do is we need to lower this voltage right here. So what could we do to our design to lower that voltage? We got several options, guys. Which ones? Could change the collector resistor. But if we raise that resistor to make it drop more voltage, then we increase the output impedance of the amplifier, which means now we won't be able to get as much out, right? You understand? So my option would be over on the base side. So what I want to do is I want to raise this. If I raise this voltage right here, then that's going to increase the current, right? You understand, right? If we increase the current, then what's going to happen? Then the 10K that we've already got will drop more voltage without changing it. So which one of these do we need to change? Well, we can make this lower. If we make this lower, we decrease the input impedance. If we make this lower, we decrease the input impedance. But what we want to do is we want to make this guy right here bigger. And that's a win-win because we increase the input impedance. So whatever's my function generator over here won't have to provide as much current, right? You understand that? And we're not changing the gain of the amplifier. The gain of the amplifier is still going to be 10. So what do we want to try there? Well, let's do it. Hit and miss. 50K would probably be way too much. Maybe 25. So let's say what voltage do we want right here? So if we want this at 6, then we want this guy right here to drop 6 volts. What current would I need to drop 6 volts on a 10K resistor? I is equal to V over R. We want it to drop 10 volts. We want it to drop 6 volts. So we're not going to guesstimate this. We're going to get pretty close with it. What's that? 600 micro, right? Pretty good. 600 micro. This guy has a typical beta of around 100. So that means to get 600 micro on my 1K, it would need to drop what? Instead of 400 millivolts, it would need to drop 600 millivolts. Okay, 600 millivolts. So that means what would I need on the base? So I'm going to take 0.7, add 600 millivolts to it, or 0.6 volts to it, right? What would that give me? 2.3 volts, right? So we need this guy right here to drop 2.3 volts. So what size would we use? So what current would be 2.3 volts? How much do we want this guy right here to drop? If this guy drops 2.3 volts, what's that? Okay, so we want it to drop 9.7, right? Is everybody okay? Okay, 9.7. So how much current through a 100K resistor would be required to drop 9.7 volts? What's that? 97 microamps. So what size resistor do I need down here to drop what we come up with? 2.3 volts at 97 microamps. And we'll use the closest standard that we got. Of course, with electronic workbench, I could use any size I needed, right? So what size resistor would drop 2.3 volts at 97 microamps?
23.7K.
So we don't have a 24K. There is a 23K. So we'll come up here and we'll change this guy here to a 23K. If they'll let me. So we'll bring up our voltmeter, we'll measure the base, and see if we got what we want. What do we want there? We want 2.3 volts. We didn't do too good, did we? What we went wrong at?
1.3.
We want 2.3 volts drop right there. Because what we want is we want 900 we want 600 microamps over here, right? All right. 2.3 minus, really? Oh, we want 2.3 right here, so you're right. So we end up with what right there? 1.3. Okay, that's not too bad then. So I'm seeing that wrong, guys. Thank you. So we got 1.2, about 1.2 volts right there. We'll see what we got. And what we'll go is, let's go over here on the collector and see what we have on the collector. Oh, wait a second. Let me get rid of this. No, we need 0.7 of a volt more positive over here. So, y'all get me confused. So we want 600 millivolts right here, right? What's that? So this guy right here is sitting here at 902 millivolts. So we got that exactly where we want it. This guy is sitting at 3.5 volts. What's that? Okay. This guy right here could be wrong. Okay, then it is wrong. So what is it? Oh, okay. It's 1.3. I can't do math. Rich said it. I can't do math. I did it wrong in my head, guys. 1.3. Yeah, 97 micro. Okay, all right. Yeah, thank you. So 10.7 here, right? Then that'll give us our current, the size of our resistor. Thank you. So we come up with a 12K, right? What was our current? 170 microamps and 107 microamps. So what we did when we did it that way, so this is the guy we usually like to play around with because this sets the input impedance. So the higher, if we look at the input impedance or the input opposition to our AC signal, it flows this way and then through the transistor and through the 1K, right? So the higher we make these resistors, we know right now it's going to be less than 12K because this guy over here is seeing this times beta. So we know in a parallel circuit that your total resistance is always smaller than the smallest, right? You understand that? So it looked like our beta, typical beta, worked out really good, guys. And now 3904 typical beta is around 100 for this transistor that we'll be doing. Are we okay? Okay, so what's going to go on here, guys, if I start doing stuff? What's some of the things that could go wrong with this guy? resistors could open. So let's go around and open up some resistors and try to anticipate what's going to happen. Okay. So what should happen if I come up here and open right here this 100K? What should we expect to happen? Now, what we should have done, let's go back here and look at our inputs and outputs before we start putting problems in here. So I'm going to bring my oscilloscope down, and the oscilloscope for electronic workbench is not really great, guys, but it should be good enough for us to see. So here's my oscilloscope. So here's your ground or your common up here. And here's channel 1 and here's channel 2. So let's come over here and we'll just use one channel right now. And we'll look at the input. So I need an input on here. So I got one. So we'll turn it on and see what everything looks like. What's going on with my scope? No, it's doing a solid big black line. So what do we need to do? We need to spread it out first before we make it bigger. We can make it bigger, but even if I come in and make it bigger, guys, it's just going to be a big black line, right? I'm sorry. So what we need to do is we need to speed my scope up. That's what we need to do, because we need to spread it out. So to spread it out, you want your scope to trace faster. So I'm going to come over here on my my time base and start making this smaller, and eventually we'll start seeing it, right? And the trigger on the scope is not really good. So here's my trigger, and we got it set on 0. So here's my AC coming in. See if we can get it. Okay. Like I said, the scope is awful. So here's my AC coming in. And we have it on 2 volts per division. Good gracious. We might have to drop this down. I might have to use something else, because I think 2 volts in is going to give us problems on the output. So what would be the gain of this guy? The calculated gain. 10, right? So we take this guy and divide it into that, so we have a gain of 10. I'm bringing 2 volts in, gain of 10, 2 volts peak in, gain of 10, right? In fact, I'm probably bringing in more than that. Let's see, so I have it on 2 volts per division, so they're giving me 1 alternation. So I'm bringing about 4 volts peak in, so what would I try to get out? What's that? Well, no, it's about 4. I have it on 2 volts per division, and this says 1, but it's undoubtedly it's not quite right. So I'm getting 2 volts, so that would be 1 volt. That right there would be 2 volts. I'm offset a little bit, so if we move our position up, if I can get it to show up. In fact, we'll just turn down the speed. So that's 4 volts in. So 4 volts in, what should I expect to get out? Times 10, what would that be? 40 volts. Can I get 40 volts out of this thing? Why? Oh, we got 12 to work with. That's exactly right. So that means we need to lower this input voltage a lot. So 10 millivolts, I got a gain of 10, that would be 40 millivolts out. So we could probably put 50 millivolts. Now, of course, what we're looking at is we're riding on top of DC, right? Can y'all see? Can y'all see what I'm talking about? So we want our scope to block the DC and pass the AC. So what do I need to do? Yeah, we did change the AC coupling, right? And there we go. So here's our input, and then here's our output. Oops, guys, I don't know what's going on. Y'all see anything we've done wrong? So I'm putting in this and I'm getting this out. Actually, our gain is, oh, I know what's going on. Sorry. So our gain will be a gain of sorry. Our gain will be a gain of 5 because to calculate your gain, we use what? This in parallel with that. So I had a 1K out there. So that should give us a gain of 5. So let's see if that helps us out a little bit. Okay, so that was the problem. I was using a 1K over there. So I was getting a gain of less than 1, right? Okay. Does this affect the bias any? Bringing an AC signal into it, should it affect the bias? Well, what's happening is I'm bringing an AC signal, and the AC signal, so if I was to come up here and I was to come over here and I have 0 volts, and then I come up here and I have this, and let's say this is 5 volts DC, and I come up here and I put an AC signal on this like this. What's my DC average going to be? My DC average is going to be right down the center, guys. So that means it's still going to measure 5 volts DC. So if everything's working right and I don't overdrive this thing, if I put an audio signal into this thing, my biases are still going to measure exactly the same. Because for audio, for every one of these, I've got one of these, right? You understand? They're just opposite of each other. So yeah, if everything's right, now if I come in and I overdrive this thing, it's going to screw the biases all the way up. Because now what's going to happen, if I overdrive it, this is going to try to go up here, and it can't go up above what, 12 volts, and it's going to try to drop down here. And now they're not going to balance each other out, right? You understand? So we can tell right off the bat if we're overdriving it because our biases are going to be wrong. So we'll do that on purpose, which means this might not be the stage that's giving me the problem. It might be the other problem. So here's my meter right here. I'm going to come over here and measure my DC right there. And what does it measure? It still measures the same thing, right? You understand? Yeah, I come over here and look at that. It still measures the same thing, right? See that? So the AC signal is not going to bother the bias. So you can mind this light struck me one time that the AC has no effect on the bias as long as the AC don't go too high or too low, right? Does that make sense? Okay. So this is what we're trying to do. We're trying to get this AC signal through here. I mean, it wouldn't be any good to have an amplifier that did not get that does not do this. So what we're going to do is we're going to come up here and we're going to open this 100K. What should we expect to happen? How can current go up? Base voltage is going to go to what? If the base voltage is going to go to 0, because what we've done is we've lost the resistor that's connected to the what? To the power supply. So I've lost my power supply on the base. That means there's going to be no current flow through this resistor right here except for AC current, guys. So what's going to happen is my base bias is going to go to 0. So what should that cause to happen? Am I going to lose my output? Well, it all depends on the input. If the input gets above 7/10 of a volt, then the output's going to turn on. But it's definitely going to clip one side, right? So let's come up here. Let's open this up and see what's happened. So we're going to come up here. We're going to go to faults. We're going to open this guy up. And then we're going to turn it on. Oh, I don't have the meter hooked up. Base bias goes to 0, right? You understand that? It says 102 microvolts, which is basically what? 0. Okay. So it went to 0, right? Everybody okay? Here's my output over here. What did my output do? Nothing. Yeah, but guys, we have a bad tendency of, if we don't see anything, people have a bad tendency of trying to see something. And they'll come over here on this oscilloscope and they'll just start turning it down. And eventually, guys, you're going to see something. Because it's AC. AC will couple through and open. Y'all understand that, right? We had a big problem with people when we used to teach computer troubleshooting. They would turn their scope down until they saw something. And eventually, in an AC circuit, you're going to see something, right? You understand? So you need to know what you need to set and what you're supposed to see before you put it on there. And this is a big thing that I try to preach, is don't use a meter if you don't know what to expect, right? You understand that? Could cause you what? Yeah, it could cause you some problems. So we did pretty good on that. So let's come up here and open. So the transistor cuts off. If this guy here cuts on, if it's open, the transistor cuts off. Now the AC signal on the base still should be the same, right? So if I move my scope back over to the base, oops, if I can make it break loose there. Make it right there. Turn it back on, Rich. So the AC signal on the base is still there. Oops, on the wrong way, Rich. But it's no longer going to be riding on the DC, right? You'll see that. Everybody okay? And then when I take my scope and put it over here, it goes right now. But if you use a real scope, you'd see something there if you turned it down far enough. So what we're going to do now, everybody okay there? What happened to the bias voltage over here? What would this voltage right here be now? What should we expect right there if the transistor's cut off? DC voltage. What's that? 12 volts. That's exactly right. Because there's no current flow. If there's no current flow, this guy right here is dropping how much volts? Dropping no volts. So I come over here and look at this guy right here and see it's sitting at 12 volts. Down here on my emitter resistor, it's going to be sitting at 0. If I come over and measure 12 volts right there, guys, I know the transistor's cut off. Right? Everybody okay? Makes sense. Okay, so what's going to happen if I come over here and we'll open this resistor right here? The 12K. What should we expect to happen? What should base voltage do? Should it go up or should it go down? So the 12K resistor is going up, and you're saying it's going to drop less voltage? Base voltage is going to go way up, guys. Base voltage is going up. it's still got a circuit up through this guy. This guy's seeing it's times beta, so we still have a circuit. This guy's going to drop some voltage, but this guy's going to be 100K and 100K. That means this guy right here should go up to pretty close to 6 volts, which means transistor's going to saturate. It's going to turn wide open, right? You understand? As wide open as it possibly can. Yeah, it's going to go way up. Now, it's going to be kind of misleading, but we know that base voltage is going to go way up. Output signal is going to be clipped. It's going to be all distorted. All your biases are going to be off. And this is the trick, guys, understanding these biases to understand what's wrong with the amplifier. So base voltage went up to 1.8 volts, which is all it can do, right? Collector voltage is gone down to 1. This is the telltale sign right here. It's what? Supposed to be 6 volts. It's setting at what? Can y'all see this? Yeah, it's setting at 1.3 volts. Supposed to be what? 6. So the transistors move way into saturation. We come up here and we look at our input signal. It's going to be distorted. Our output signal is going to be distorted. So let's look at our output first. Should be clipped on the bottom. If I could get it to trigger. Yeah, see how weird it looks? Yeah. And then our input signal might even be distorted. Because we've changed our input resistance. What's that? Oh, okay. Sorry. I see what you mean. In fact, I flipped this thing around. What did I do? Oh, I see what I did. Hold on. Need to get rid of this guy, right? This guy needs to come right here. So this guy was right. My other guy was wrong. What's that? Not really. We'll have to come up here and actually see what's going on. No, it still looks okay. So if this guy right here opens, the transistor does what? Saturates. If this guy right here opens, the transistor cuts off. Are we okay? Okay.
Every time.
Huh?
Every time.
But you can tell by the bias. So over here, if we know this voltage right here, we know if it, so we expected 6 volts over here, and this guy had dropped down to 1.2 volts. So we know the transistor had moved toward what? Way toward saturation. Right? Okay. Okay, so what should happen when this guy, if this guy right here opens? Yeah. Because we have no voltage to work out with, right? So we'll come up here and we'll open this guy, see if we're okay. Yeah, so this base voltage, the base voltage is going to be weird. The base voltage is going to go down. Now, why did it go down? No, with this resistor right here opens, the base voltage is going to go down from what we figure it's supposed to be. Can anybody tell me why? So this resistor right here is seen as times beta. Beta is IC over IB. We just lost IC, guys. So we lost beta. So now this guy here is seen as a 1K resistor. It's not seen as a 100K anymore. It's seen as a 1K. That 1K is setting the base voltage right there now. Not this right here. Right? You understand? So this is where it's going to get kind of weird because the base voltage goes down. Right? You understand? But the transistor's still going to move toward cutoff. Why? Because it's got no collector current at all, right? So let's see that. So let's check our base voltage. Well, what do we expect it to be? Yeah, that would affect it. Normally you don't have, I thought I put none. It's very unusual that you would have two resistors inside this thing go bad at the same time, unless you put it in there when you're working on it. This happens a lot with people that don't know what they're doing. They end up putting things in there that they don't understand. Flipping switches are not supposed to flip. I'm talking about our troubleshoot class yesterday. So, of course, that could have been the problem. But what I'm saying, what I was telling my class, flipping switches okay, but you need to understand what those switches do before you just do what? Before you start flipping them, yeah. So we do need to find the data sheet on that thing. What's nice about the Festo line is they gave us the data sheets on every component. Amatrol didn't do that. So we get part numbers and stuff like that and try to look that up as we go along. So here we go. Let's turn this thing on. Base voltage has gone down to 653 millivolts. We was expecting 1 over 1 volt there, right? Now, why did it go down? Because we lost IC. When we lost IC, what did we lose? We lost beta. So this resistor right here is setting the base voltage. Move up here. What we're going to measure up here at the collector? 0. Notice we get some weird stuff coupling through. 100 millivolts, right? We've lost the reverse bias, so what we're doing is we're getting a little leakage through that diode right there. Are we okay? And what should we see down here? Should see 0.6 of a volt less than what we had there, so we'll see what we measured there. So see what happened? Everybody okay? Makes sense? Good call. Most people miss the beta. And I even found this out playing around is what was going on. And when we first did that, when I first taught it, I said, well, the base voltage shouldn't be affected at all. And then it was affected a lot, and we had to figure out why was it affected, right? And of course, we eventually figured that out. So we'll take this out of this one, and we'll open this resistor right here. So what should we expect to happen now? Beta's gone again, but also we're dealing with infinity on that side. So infinity. So our base voltage should go up just a little bit, because this guy over here is not in the circuit at all anymore, right? Base voltages will go up a little bit. Transistor should do what? Cut off. Yeah. If you don't have emitter current, you don't have collector current, right? You understand that? So no emitter current, no collector current. So transistor should cut off. And we hadn't looked at the AC signal. So here's our base voltage. It's going to go up a little bit, but not very much, because we anticipated that, right? We ignore that resistor over there anyway when we calculate that. We will get some voltage right here, but it's going to be just coupling through that diode through my load. Let's see what's going on. So here we have 12 volts. We expected that, right? Transistor's cut off. And something's going on with our simulation because it's measuring 4 volts there. I don't know where the 4 volts is coming from. I think something's wrong with the simulation. This is going to be, it's going to be a voltage there, but it's going to be really low, right? You understand? Oh no, that's where it's coming from. It's coming through my meter because this resistor right here, no, I don't know where the 4 volts is coming from. Well, it's got to be wrong, right? Everybody understand that?
So that's what we read almost right?
That's probably right. Oh, there it is. Yeah. So that's what it should be. And of course, what's it doing? Oh, crap. So the simulation is off. Oh crap. Click. No. Not as far as moving things around. You can if you delete something, you can undelete it. This is fun to do with a mouse. Okay. So what else could go wrong? So we've looked at all the resistors. We've got 3 more components in here we need to look at. So let's take this gripe off. Capacitors could be bad, right? The problem with capacitors is they could either they could go wrong 3 different ways. They could short, or they could open, or they could become leaky. That means they act like a resistor. So what do you want to do first? Huh? Yeah, but what do we want to do first? So we can short it, we can make it leaky, we can open it. So let's open it. What should we expect to happen to our bias? Nothing. Right? Bias is going to be perfect. So right off the bat, with the bias perfect, we know the problem is with the transistor. But of course, what we would see when we come here with our oscilloscope, this would be hard to find. Troubleshooting amplifiers, guys, is just about going to take an oscilloscope. So we got nothing here, right? Then when I go right here, we have our waveform. So we know right off the bat, nothing on this side, something on that side, then we know it's open, right? Now in real life, you'll see it'll couple through and open. So if you turn your scope down far enough, you will see something. So you're not looking for something. You're not looking for anything. You're looking for whatever you fit, what's supposed to be right? So what should happen if we short this sucker? So what's my base voltage going to go to? My DC bias voltage. Is this going to affect the bias voltage? What's this going to cause my base voltage to go to? No, when it's short, it acts like a piece of wire. So how should that affect my base bias voltage? DC flies through an AC source like it's not even there. So AC sees a DC source as a piece of wire. An AC signal a DC signal would see an AC source as a piece of wire. Huh? No, it's going to be, the base voltage should go to 0. It's going to drop to 0. Or pretty dang close to it. Now it all depends on the input impedance of the actual source itself. Yeah, but it's microvolts. Microvolts on a meter looking at DC and is a nothing, right? You understand that? So yeah, so it went down to 0, which is going to cause the transistor to do what? If we got a base voltage of 0, it's going to saturate. If we got a base voltage of 0, it's going to saturate. If we got a base voltage of 0, it's going to saturate. It's going to cut off. I kept trying to get you to change your answer. Okay, so 12 volts. No base voltage. What cuts the transistor on is base voltage. We got to have base current to cut it on. If I've got 0 volts on the base, I have 0 base current. If I have 0 base current, the transistor's going to cut off, right? So I come over here, I measure 12 volts over there. I come over here, I measure 0 volts over here, or microvolts over here. Then I know I got a problem. But this is one of those two scenarios right here. So what caused this to happen before? That 100K open, so my 100K could be open, or that guide or my input capacitor could be what? Shorted. So you got two things that could happen. All the other things, we knew exactly what it was. But this right here, this would be two things that could go back. Right? That makes sense? Are we okay? Now, leaky is going to be really strange because leaky means it's what? Well, now it's going to act like a 100 ohm resistor. So what I've got now is I've got a 100 ohm resistor. I got my input feeding to a 100 ohm resistor. So it's going to cause my base voltage to go down, right? You understand that? Let's see this. So it's measuring what? Yeah. So my input bias voltage now is, I'm sorry, it's going to make it go way down because it's seeing this is 100 ohms. It's seeing this at 0. So now that 100 ohm resistor is setting my bias voltage. So what two things cause this to happen? We've seen this before, a very low base voltage. Not the 12K. The 12K caused the base voltage to go up, right, and move towards saturation, right? This guy moved toward cutoff, but this right here went to basically 0 volts, right? What happened though is when we come over here and we open this resistor right here, then it caused the base voltage to go down a lot because we lost beta, right? Remember that? So when this guy's real low, of course, we still have millivolts, right? You understand that. A while ago, when we opened this resistor right here, it went to microvolts, right? You understand that. So it could either be this guy or it could be that guy. We okay? Yes or no?
So you're saying the leakage, is it going to be?
Well, it all depends on how much leakage you have. So if I come up here and make this 1,000 volts, 1,000 ohms, then my base voltage is still going to be low. But notice now it's still in the what? Millivolts, 110 millivolts. Okay. So the higher this guy is, the more leaky this is, or the less leaky it is, then my base voltage keeps going up, right? You understand? So let's go here and take the leakage out of this. So when you measure a capacitor with an ohm meter, what should it measure? Should measure what? Infinite, yeah, unless it's a big capacitor. What happens, a capacitor, it stores DC, right? You understand? So when I charge the capacitor up with my meter, we'll do this. We'll just charge one. I think I got a. Oops. So I got a capacitor up here. This is a. So I'll put it on ohms because we want it to act like a source, right? You understand that? And then we'll come over here and I'll take my capacitor. Take a capacitor I have up here. This is a. This is 100 microfarad. And so what we're doing is we're seeing it charged through the meter. But all the smaller it is, so when you're dealing with these coupling capacitors, they're going to be a pretty good size because we want them to have very low opposition to AC, right? You understand? So this is 100 microfarad. So it charged up, but eventually it should go to what? Yeah. Now the smaller it is, you get these little small capacitors, they're going to charge up. They'll measure open right off the bat. But these big capacitors, and then we swap them around. You'll see it actually go negative because the capacitor actually was charged up. But these big capacitors like this, you can actually check to see if they're good with an ohm meter. You should see them what? Charged, but eventually they'll go to what? Now this guy here is charged up to whatever voltage my meter puts out. So what happens when I swap it around, notice I get minus ohms. See, minus ohms. And then eventually it'll turn positive and charge it back up in the other direction. So it's real easy to check a capacitor. Now, y'all understand, if it checks good in circuit, we assume it's good, right? You understand? If it checks bad in circuit, what do? We isolate it. We raise one lead. We unsolder one of the leads and raise it up, right? You understand? And we check it out of circuit. You don't have to pull it completely out of circuit. You just need to isolate one of your leads. That makes sense? So this resistor right here would be safe if we turned it off because the transistor would be cut off. So this should measure about 1K. This should be okay. This guy right here, these should be okay because they're not in parallel with anything. So you should be able to measure all the resistors inside a transistor circuit with an ohm meter. Right? You understand? Of course, what's going to happen is we're going to get a bad measuring over here because this guy right here is leaky, right? You understand? So we can measure it, we isolate something, we check it, right? You understand that? But we know it's either going to be what? This guy or this guy, right? That makes sense? Okay, guys, where do you want to go next? Oh, I thought I took it out. We can play around with this capacitor right here. What's going to happen if I open this capacitor right here? In this circuit, nothing's going to happen. Because we're treating, this is a resistor, right? You understand? Normally, so what did we use when we calculated our gain? We calculated this at 5K. Oh, I'm sorry, it will happen. So what happened? Okay, so our bias, when we calculated our bias, we ignored this resistor right here, right? Because this capacitor was blocking the DC bias. So what we're going to do is we're going to short this guy right here, And now my DC bias at this point right here is going to be set by this circuit right here. So what should we expect this to do? So what should we measure it? Let's go back. Let's do it. So is it going to go up or is it going to go down? So let's see what effect it has on the base voltage. What are we expecting on the base? 1.23, so it didn't affect that at all, right? So what should we expect right here? Should it go up or go down? And why? Well, when we calculated that bias voltage, this guy right here was an open. This guy here was an open to DC. So that means that this current that was setting that voltage right there, this resistor, we just ignored it because bias is a DC voltage, right? You understand? Yes or no? When I short this resistor right here, that 10K is now part of the circuit.
Okay, so they get some of the voltage.
It's a path. So what happens, we have two paths now. We have current flow here going through there. We have current flow here going through there, which means the 10K is going to drop more voltage. If the 10K drops more voltage, that's going to be less DC right there, right? So I expected it to do what? Go down, which is what it did. Now, what could cause this to happen? Well, we could have a problem. We could have a problem on the left-hand side, but that's really easy to check. Well, I come over here and take my meter, and I move this guy right here over to there, right? And it measures exactly what it's supposed to measure. Because the transistor's still conducting, we still see this as times beta, right? I come over here, and this guy right here is a lot lower than what's supposed to be. Which means what? The 10K is dropping more voltage. Now, what could cause that to happen? Well, we could have more current over here, but when I come over here and look at this guy is sitting right where it's supposed to be too, right? You understand? Right? Okay. So it's okay. This guy right here is low. So what does that mean? Well, it means the 10K is either got bigger or there's more current flow through it, right? And of course, the problem here would be the 10K could be bigger, right? So we got two problems. The 10K could be what? Bigger, right? So its resistance could have gone up, or the capacitor could be shorted. And how could you check that? You could check this in circuit. It's just like shorted capacitors. We can check this in circuit. Put my ohm meter up there. Right? We don't need to pull one leg. It's going to measure, well, yes, but it's going to measure 0 ohms. Right? We okay? But you're right. Once we measure 0 ohms, we pull it up, it still would measure 0. What would happen if it opens? What would happen to my bias voltage? Everything, yeah, bias is going to be perfect. This amplifier will be fine, right? But what we would do is I'll come over here and measure this guy. Just measure right where we want it to measure, right? To understand. Of course, if that's measuring okay, then I have no need to even go over there because there's no way this guy's going to be right and this guy over here be wrong, right? You understand that? So the only thing I'll be able to do is find this with an oscilloscope. We measure right here. It measures 0. We measure right here. the gain is going to be a lot higher right here than what it's supposed to be, because now it's a gain of 10 instead of a gain of 5, because we lost our load, right? It's not clipping, the scope is just doing that. So now we're getting a gain of 10 instead of a gain of 5. Are we okay? So what should happen if this guy becomes leaky? So it's 100 ohms. So is the collector voltage going to go down, or is it going to go up from what we expect? It's going to go down because we've added that other current path, right? So we've added another current path. So that means we've got this guy here is dropping both this current and that current. So my collector collector voltage is going to go down. So it's down to 3 volts. Of course, the bigger that is, the higher it's going to be up, but it's going to be a lot smaller than what we expect. So what could cause that to happen? Well, we know there's a couple of things that could cause that to happen. What was the other thing that caused it to go down? This guy right here opened. This guy right here opened, right? Because if it opens, base voltage goes up. But we notice now we have no problem, because I measure low right there. The next thing we would do is we would move over to here. It's measuring what it's supposed to be. So if this guy's measuring what it's supposed to be, we know that the 12K has no problem, right? You understand? So we move over here. So the base voltage has gone down. Well, this guy should have a problem, but I just screwed up. We measure here. This is right where it's supposed to be. So I turn it back on. Oops. I know y'all need a break, so because we got one more problem. There we go. So this is where it's supposed to be, right? You understand that? So that guy's okay. So we know this guy's conducting what it needs to be. This guy right here is low. So there's only one thing that could cause that. Either this resistor's gone up in value, right? You understand, or the current's gone up. Are you okay? Okay, what's the next thing that could go wrong? That would be one of our first steps of troubleshooting. One of our first steps of troubleshooting, guys, right off the bat, is you check power. You check to make sure your power supply is okay. So we're assuming right now, we're troubleshooting this amplifier. We're not troubleshooting the power supply. We're troubleshooting the amplifier. So what other component could go bad? We played around with the load. The load could be bad. You're right. If we change the load, we change the gain. But we'll look at that. Let's work inside the amplifier. Transistor. Okay. Y'all take a break, guys. Take a 2-minute break. So collector to base. We got it short. So what should we expect to happen? So what's my base voltage going to do? Is it going to go up, or is it going to go down? Why? You're right. Well, you got a 10K in parallel. You got a 10K in parallel with a 100K now, right? You understand? So it means it sees it as less than a 10K, which means it's going to drop less voltage. So my base voltage goes up. Turn on simulation, Rich. So it's sitting at 1.67 volts. Now the kicker, we know it's higher than what it's supposed to, but this is the problem we get. We're expecting what, 1.3, and it's set, so it's not that big a deal. So we say, okay, that's okay. Even though it's not, then we move over here, right? Then we say, okay, let's see what's over here. And that's wrong. 1.7 volts. This is fun to do with a mouse, guys. So what do you notice about the voltage on the base and the voltage on the collector? They are exactly the same. Exactly the same. 1.6637 volts. Might be better if I disconnected at the meter and then reconnected. 1.6637 volts. There's only one reason that could be possible, and that's what? If they are connected together. Okay? So this guy here is a little high. This guy right here is probably going to measure about 0.6 or 0.7 of a volt lower. It does, right? We look at our signal. Let's look at our actual AC and see what it looks like. Let's see if we're going to be able to see this. So we'll move this one up. So that's our input. And here's our output. Let me find it. So what do you notice about the input and the output? They should be exactly the same because we got it shorted between the collector and emitter, so we're not getting near the gain that we expected to get, right? And not only are they together, they're also in phase with each other. On a common emitter, we're expecting a 180 degree phase shift. Oops, wrong one, Rich.
You got bigger, Rich.
Well, I'm doing the wrong one. And I'm still doing the wrong one, guys. Still doing the wrong one. Somebody's going to have to take care of me. So not only are they the same, they're also in phase with each other, which is another telltale sign is that they're supposed to be on the common emitter. They're supposed to be 180 degrees out of phase, right? Are you okay? Yes, no? Okay, so let's short 2 and 3, which would be our. What's this going to happen to our base voltage? Yeah, base to emitter. Is it going to go up or go down? 50-50 chance. We did collector to base. Now we're doing base to emitter. So the 100K was seen as times beta. Well, with a short circuit, the 1K was, when it was working, the 1K was seen as 100K because it's times beta. Now I got a piece of wire connected to there, so it's going to be seen as a 1K. So instead of this being 12K down here, it's going to be less than 1K. which means this voltage here, if this guy here goes down, voltage there is going to go down, voltage here is going to go up, right? You understand? So base voltage is going to go down by quite a bit. When transistor cuts off, because we have no collector current anymore, so we have a short right here. Transistor cuts off. Here's my input. My input still looks okay. My output is cut off, right? Measure right here, it's probably going to measure 12 volts DC. We'll look at that in a second. But our base voltage is, our base has dropped down. Ooh. What's it supposed to be? Supposed to be 1.3, right? Let's see what's going on right here. It's not shorted. Because right here we're measuring 1.3 volts. And if it was shorted right here, we would measure 1.3 volts. But it's measuring, everything's measuring okay. So the simulation is wrong. Y'all see what I'm talking about? Because if I had a short, if this was a true short between here, that means whatever voltage I measured there would be exactly the same thing right there. When I come up here and look at this, so this simulation is off. Here it's measuring 1.2 volts, which is right. And here it's measuring 1.1 volt, which is right too, right? You understand? So the simulation is not working. You understand how I know that? Yes or no? They should be the same because it's a piece of wire. So if I came over here and I had this, and now I've got this. If I measured 5 volts right there, what would I measure right there, guys? It's a piece of wire. It measures what? 5 volts. Well, you can see the simulation has definitely got a problem. I even cut it off and cut it back on because it gave us that problem a while ago. And see, this is measuring about 7/10, and so see, it's measuring 1.1, and this guy here is measuring 1.2, 1.3. So they should be exactly the what? Same, yeah. Yeah, because it's a piece of wire. If you got a short, if you got what we call a short, and this is the problem with bipolar transistors, is they can go bad different ways. So a resistor will not short. I've never, well, I'm not going to say that. I've never seen a resistor short. I've seen a resistor get shorted around when people do something stupid, right? You understand? Like they'll be soldering and they'll leave the leads too long on the bottom side of the board, and when the board gets pressed down, two component leads touch together. Or they're soldering, they splatter solder across the trace and short things out like that. But I've never seen a resistor short. I've seen the resistance go up, and I've seen it open, right? But I've never seen a resistor short. But capacitors, they short, or they open, or they become what? They become leaky, and that's the same thing true with any solid state device. It can go bad 3 different ways. But a short is pretty easy so even a diode, if a diode is shorted, you measure what you measure on the cathode would be exactly what you measure on the anode, right? You understand? Exactly, not a millivolt difference. And that would tell you that the dang thing is shorted, right? So every solid state device, even when it's forward biased, is going to drop a voltage. So that means if I come over here and I saturate this transistor, even when it's saturated, it's going to drop a voltage between the collector and the emitter. It will drop a voltage. If I measure exactly the same voltage on the collector that I do on the emitter, it means that dang thing is shorted collector to emitter. And you see that happen all the time. So I don't know if the simulation, the bias measures okay, except when I go right here, this bias is all messed up. So when the guy did this, he didn't do something right, quite right. So I don't know what's going on here, because all your emitter current, if this is shorted, all your emitter current is going this way, and if all your emitter current goes this way, then that means what? There's none going to go that way, right? You understand? So this guy right here, we should measure 12 volts right there, and we're measuring like saturation. So the simulation is not right. And I can understand that. I wrote programs before. So let's short it collector to emitter. So this is going to be easy to identify, because now this is going to be a 10K in series with a 1K, right? You understand? So this is going to drop 1/11 of the voltage. This right here is going to drop 10/11 of the voltage, right? But it's still going to be a telltale sign in that if the simulation works right. If I measure right here, this is going to be way down. See there? So the simulation is not 1 to 3. Oh, I'm sorry. I don't want 1 to 3. I want 2 to 3. So this might be right. See? So that voltage goes way down, right? But the telltale sign is I come over here and measure right there. And what does it measure? Yeah, it's going to measure exactly the same. See that? And then the base is still going to measure about 7/10 higher than that. So it measures okay. So that's about it, guys. And y'all did a pretty good job on anticipating what this thing would measure if things happen. And basically, we depend on what it would depend on to determine what's wrong. We depend on the bias. If the bias is right, and we're not getting anything through the amplifier, then either the amplifier is not getting an input or something's going on with the output, right? You understand? If the bias is wrong, then something might be going wrong with the. Let's do one more thing, and then we'll let y'all go to lab. Let's overdrive the thing.
Overdrive?
Yeah, we're gonna put too much into it.
Overwork?
Yeah, we're gonna overwork it. You can hear people do this all the time. They overdrive their amplifiers, and they get very distorted, especially these power amplifiers. They'll get a power amplifier, and then they'll run it off the preamp of their power amplifiers run different. You can set them up for high impedance inputs or low impedance inputs. The low impedance inputs, you want that, normally you hook that to the output of your radio in your car, because you're getting a lot of voltage out there. If you hook up on a high impedance input, that means you're probably running your power amplifier off your preamp. You know, that makes sense? You understand what I'm saying? Yes or no?
The preamp, it's kind of like an.
Yeah, what we do is we start off coming in with a high input impedance, right? You understand? Because we don't want to load the signal source. By the time we get to the end of the amplifier, we want a low impedance amplifier because we're trying to drive a lot of current, a lot of load, right? You understand? Well, what we do is we go through several stages. All your controls, your balances, your volume controls, are they going to be in the low impedance side, or are they going to be on the high impedance side? Well, they're going to be on the high impedance side, because you don't want a rheostat this big controlling your volume, right? You understand? You want to be able to control a very little voltage to get a lot of gain. So what we have is normally amplifiers are divided into two sections. They're divided into what we call a preamp, and then they're divided into a power amp part. So when you go out and buy a power amp, you're getting the second part, not the what? The first part. Well, if you drive your power amp on the output of your radio, then you're going low impedance into low impedance, right? If you drive it on your preamp side, and a lot of radios give you a split, they'll have a jumper on the back where you can unjump it and disconnect the power amp on your radio and bring your power amp into that. Then you're going to be hooking up your power amp to run as a high impedance amplifier, right? Does that make sense? So y'all get a little feel of what's going on. So what we want to do is we take the preamp is going to be where all your controls are, and your power amp is just going to be in there for what? Power, right? Y'all understand that? So I don't know how if I got off on this conversation. How did I get off on there? Huh? Yeah, the amp. We're talking about stereo amplifiers, but the problem of an amplifier is we want to get a what type of gain out of these things? Power gain. Yeah. So to get a power gain, we're going to have a source for the signal, and every signal source that I know of is basically high impedance, right? You understand? And then we're going to have to eventually go to a low impedance output to get the power out. So we go through stages in an amplifier. We go through stages. Used to, you could actually see them. We've got a power amp over there. I need to go find it where it's burned up, but you can actually see the two channels come down through there and how they work through that thing. Power amps are still use a lot of discrete components. Your radios, they've been around for so long, then your preamps and your power amps are in what? In one integrated circuit. So now if you got a radio in your car that goes out, then odds are you're going to do what? Replace the radio, because they're just about unrepairable. Power amps, though, if you got the schematics on the power amps, those are still very repairable because they still use a lot of what we call discrete components. There was one thing that we left off this, and this was, what do we need to do to increase the gain of this thing? Could do that, but another technique we have is to bypass this capacitor right here. And we call this a bypass capacitor. So these capacitors are called coupling capacitors, right? Everybody okay? Because they couple the signal in, and then they couple the signal out. They keep the bias in because the capacitors block the DC, right? You understand? This guy right here, it causes your AC signal to bypass that resistor right there. So instead of the gain being set by this resistor, the gain is set by this thing we call RE prime, which is really, really low. So RE prime would be equal to what was our collector current? What's that? 107 microamp. So we take that and divide that into 20. So it's 25 milli. It's 25 milli over that number, and that'll give us RE prime. 25 millivolts over IE. 233 ohms. Really? $2.3? 233? I'm not saying it's wrong. I just thought it would be a little. 233 ohms. So the gain of our amplifier is going to jump up to 233 times beta, which would be 100. That would be what? Something's not coming out right. What's that? Yeah, something's not coming out right, guys. Because it should be a lot less than this guy right here. So let me see what I'm doing wrong. Or IC, we use those as the same thing. 25 milli divided by our current in our emitter. Huh? 25 milli divided by 600 micro. There you go. I was expecting it to be a lot less than 1K. So the gain of it is going to be 4 times 100. So that'd be what? That's still not right, guys. Oh no, that's 100K. This is seen as 100K. So now it's going to be seen as 44K. Right. So this is going to be 5K divided by 44K. Nope, something's still not right. No, that's my input impedance. So it's going to be 5K divided by 44 ohms. So what would our gain be? So I had the input impedance formula on my mind. So the gain we should expect now would be 5K, which is our output resistance, over RE prime. What was RE prime? 41? Okay, 42 ohms. So what should our gain be? Okay, so it's going to go up to almost 120, right? So we're going to have to really play around with our input. Now what we did when we bypassed it is we sacrificed input impedance. So that means my source is going to have to drive more current. So what's this guy right here called? This is called a bypass capacitor, right? Everybody okay? So we're going to have to take our input way down. So 10 millivolts times 100 and, what would you get? 100, 120, what would that give us? We can't even put 10 millivolts into it, I don't think. What would the output be? A gain of 120, 10 millivolts times 120, what would that give us? Huh? 1.2? Okay. So let's see what the gain looks like. It's usually about twice of this, so it's actually 20, I think 20 millivolts of what I set over here. So this thing is kind of misleading. Let's measure it if we can. What I'll do is turn off the simulation and try to grab it. $20 millivolts per division. Yeah, so it's about, looks like it's 20, it looks like it's about 40 millivolts. So this guy right over here is not near as right what it needs to be. And also another thing's wrong with the simulator. So what's the names of these guys? These two guys are called what? Coupling capacitors. This guy's called what? What do we bypass for? Increase the gain. What do we do? So instead of this being seen as 100K, this is going to be seen as a 44K, right? So what's going to happen is it's going to lower our input impedance. If we lower our input impedance, it means this guy here is going to have to provide more current. Okay, guys, I think we covered the common emitter pretty good. Y'all got any questions? And this is troubleshooting a common emitter, so we tried to go through all the scenarios we could possibly go. I know we probably missed some. Any problem? Okay, guys, y'all go left.